So, when we get finally near the end of the last lesson, the real question, which paradigm is best? Is there a best paradigm? In fact, in our experience, there is no best paradigm overall. Each paradigm is actually best for certain kinds of problem. Logic programming like Prolog is very good for transforming complex data structures. Things like regular expression languages are just a subset of that. For example, object-oriented programming is very good for applications that have a lot of knowledge, organizational knowledge, declarative knowledge, whatever knowledge, structural knowledge that has to be encoded in how the application works. And inheritance can encode that knowledge, and polymorphism can make sure that even though we have this large encoded structure, that each part is only focusing on one thing. So object-oriented programming is very good for that. And in fact, it's possible to combine different sets of concepts to form kind of new hybrid paradigms if one needs to do several things together. So it turns out that each set of concepts that's embodied by a particular paradigm is actually best for a certain kind of problem. We call this the paradigm paradox, because it might seem that having more concepts is better. What could be worse? But in fact, it's not, because more concepts means that reasoning, testing is more complicated. The program does not obey simple laws, but will obey more complicated laws. It will be harder to design, and maybe the simpler laws are exactly the ones that you need. So we say that more concepts in the paradigm is not better or worse. It's just different. Each paradigm is just different from the others. Functional programming is just as nice as object-oriented programming. It's just focusing on a different set of problems. And in fact, in real situations where you have big programs, where you have to solve many things, you will need both, and you will need many paradigms. So if you look at the conventional boundaries between paradigms, we have Java is an object-oriented language. Boom. Haskell is a pure functional language. Boom, etc. These boundaries are in fact artificial. They are solving the problem opposite from the way it should be done. Instead of focusing on the concepts, you should focus on the problems you want to solve. So instead of saying, we want this particular theory and this theory is what we want, no, you should say, we want to solve a certain set of problems. And what concepts do we need for that? That should be the question. So a language like Java, which is almost completely just object-oriented, this is in fact too limited in practice. And in many cases, Java people spend their time inventing other concepts and putting them in libraries and encoding them and so on. Lots of new things built on top. And so Java programs are unnecessarily complex. So a more recent language like Java combines several paradigms. It's functional, it's also object-oriented, and it's actor-based, using message passing for concurrency. So this is better. This means that Scala lets you pick the concepts, the right concepts for the problem at hand, better than Java. So a big program almost always needs several paradigms. So this is why you need to know it. And this is also why a good language should support several paradigms. This is hard to do. This is hard to do for an industry language because of legacy code. It's very hard to change existing things because of all the legacy code bogging things down. So really the way to do it is to have new languages. Somehow you do need new languages. So at some point the pressure on the old language is too high. It cannot follow anymore, and a new language will break free and be able to do more. So for example, Scala with respect to Java. So Scala and Erlang are moving in the right direction. They are integrating more concepts, whereas Java and C++ are very bogged down by legacy code. They are trying. Adding lambda expressions to Java is a good idea, but it's very hard to do because of all the organizational constraints that have to be satisfied. So in this course, we used a research language called Oz. So we did not use an industrial language. We used a research language exactly because it was designed in a well-factored way to support many paradigms, and because it did not have the legacy problem, it could do so. Okay. In fact, those ideas are moving to industry. For example, looking at the concurrency, deterministic concurrency ideas. So let me give an example to make things more concrete. I'm going to talk now about a fairly famous machine called the Ericsson AXD 301 ATM switch, which contains more than 1 million lines of Erlang code. It also contains about 1 million lines of C++ code. But let's just talk about the Erlang, because the high-level, high-availability distribution structure is defined at the Erlang level. Now, Erlang is a language that is concurrent by default. You create very many concurrent processes which are very fine-grained. It is asynchronous by default. You're sending messages, you do not have to wait for the reply. It is multi-agent by default. You create very many small-grained concurrent entities. If you compare this to Java, which is sequential and monolithic by default, if a part of a Java program crashes, the whole program crashes. It is synchronous by default using RMI. It is doing shared data by default. It turns out that Erlang is a much more appropriate paradigm for a system like the AXD 301 than Java. And in fact, one can say that object-oriented programming is the wrong paradigm for internet programming. In fact, it's not solving the right problem. The concepts of object-oriented programming are solving other things. They might be good for business applications, but they are not good for internet. So for internet applications, you need other concepts. So such as isolation, concurrency, asynchronous messages, high order programming for factoring. What's relatively unimportant for the internet aspect of the language, so the distribution, fault tolerance, is inheritance, classes, methods, UML diagrams, monitors. These are not solving the problem. If you look at the graph here, this graph in the middle is showing the behavior of the AXD 301. So here on the horizontal axis, we have the offered load. So we offer a certain load, and on the vertical axis is the actual throughput that the system is sustaining. And you can see that if the offered load is small enough, then the system can follow. It's following, the throughput is increasing as the offered load is increasing. At a certain point, when you get to the maximum here, 150% of the maximum, then the throughput reaches its maximum. Now, if you keep offering more and more load, the throughput will go down very gently. It's a very graceful degradation. And this is a property of Erlang programs, that they will not crash and burn typically when they are overloaded. Because of the fine-grained concurrent structure, they will be able to absorb the extra offered load and gracefully reduce the performance, even though internally they are highly overloaded.